types, and then they were different. You know, the iOS and the Android were different. Where I was like, okay, there's got to be a better way to do this.
Well, how does it deal with the devices like the accelerometer and microphone?
So you still have to like go into each. So
Okay.
it has the folder structure for each app, and you can go into each one and like allow the permissions for whatever you want to use.
Okay.
But you can still access all that data from the microphone, accelerometer, and all that jazz.
I see.
And utilize. It's pretty useful.
It's kind of neat as an idea that you can write an app once.
Yeah, that was the whole thing to it. There are some nuances between it, you know, that some things will only work on one platform or the other. But
Oh, I'm sure.
but if you work around those, it's not too bad.
I'm sure there are a few nuances to that.
I always associate Apple with communism. They want everything to be controlled their way.
All right. Cool. All right. So let's go ahead and get started. We have 3 classes left, and I know I'm going to use one of the classes to review the final exam. Okay. So maybe I can do something like this. Okay. So maybe I can kind of blend all of those topics kind of into one. So let me start with the exam from last year, so that you guys can see kind of what what kind of question I asked last year. Okay, so last semester is fall 16, and this is the final exam. There we go. Okay, so the final exam, at least from last year, revolved around the Astar algorithm, which I'm really, really hoping that we can actually get through in this class, because this is one of the really kind of interesting algorithms. I don't have enough time to cover graph algorithms and tree algorithms and stuff like that, but Astar is one of those things that I really want to get through. So the algorithm itself is already known. Okay, I include it as a part of the exam, so people can just refer to the algorithm. And then the questions involved. The first one is just following the algorithm. So I need people to show me all the computations. So they have to trace the algorithm, so I can see how the data structures got updated. Basically not exactly line by line, but iterations by iterations, to solve the problem. So this may not be a bad idea to start today's class, is to look at the Astar algorithm from the questions perspective. So question number 1 is really just asking, okay, how do we apply the Astar algorithm in order to solve this, so that we can find the shortest path from a particular vertex to other vertices. The other questions, they're all related to the Astar algorithm. This one is asking, use proof by induction to prove the theorem of blah, blah, blah. Okay, so we might get to that today. We probably won't be able to get to this one today. So question number 3 is, imagine you're teaching cisp440 and you want to make a resolution homework assignment. So in this case, I'm asking the reverse, which means you are going to ask a question. Create a CNF that needs exactly 3 resolutions to reach contradiction. And then question number 4 is a relation question. So I asked people to draw a directed graph. So it is it's digging up old concepts that we have talked about, relations, functions, and whatnot, and apply those concepts to graphs. Okay, so we will talk about graph in these 3 classes, because that's one of the more important topics that we have to get through in cisp440. And then question number 5 is, given the theorem of Q2, question number 2 is true, prove that the modified Astar algorithm cannot get into an infinite loop and must terminate given the set of vertices has a finite number of elements and the cost of each edge is non-negative. So once again, we are using proof by induction, proof by contradiction. So those things keep coming back, okay? Because those are actually important concepts when we want to prove that your algorithm is working correctly. So what we'll do today is we're going to start with the A-star algorithm. We'll talk about what is a graph in general, and then we'll just go ahead and trace the algorithm to answer question number 1 of the final exam last year. All right? Is that okay so far? Okay. And also, by the way, in the master theorem, remember master theorem that we talked about last Thursday? How we found one case for the first case, we found like at least 2 algorithms that fit in the second case. And somebody asked me, what about the third case? Well, as far as I can find, there are no well-known algorithms that fit into the third case. Okay, but there is a third case. I looked at all the assignments, all the exercises, all over the web, and they just say, okay, here's A, B, and C. Okay, which class of algorithms does it belong to? So you're just really just checking, testing, comparing to find out which category it belongs to. And to me, that is just dry, boring work. Okay, because it's not related to something that we already know. It's not like you're applying it to binary search. You're not applying that to the search, to the sorting algorithms that we already know. You're just, oh, these are the numbers. Let's do these, tricks. Find out which category the algorithms belong to. And that's about all those other exercises were about. Question? Yep.
Then how did they come up with the third case?
Well, mathematically, it is correct. In other words, it's all based on the original equation. The original equation is T of n. In other words, how much time does it take to solve a problem of size n, right? So the original problem says, if you can break up the large problem, which has a size of n, into A, which is a certain number of problems, subproblems, and each subproblem has a size of n divided by b, okay, plus the actual amount of time, not counting the recursion, but the actual amount of time for each iteration, for each invocation of the function. It takes f of n time to finish that. That's the overhead for each recursive call. Okay, so this is just expressing a very broad classification of recursive algorithms. But there are algorithms that do not fall into this category. Like Fibonacci does not fall into this category. Factorial does not fall into this category. Okay, with linear search, we kind of have to bend it a little bit to make it fit into this category. Okay, so by looking at A, B, f of n, and a c, such that c blah 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 blah. Remember what we talked about last time? So c has a certain criteria. I think c is either less than or equal to log b of a. Remember that? Okay, and then this c is used as a power of n. Okay, and it has to do with f of n is big theta of n to the power of c, or log to the power of some log k to n to the power of c times log k to log k of a. Okay, but there's an equation. Okay, there's an equation. You only have to find the c, and then based on a, b, c, and k, you can make a classification of, okay, how do we figure out the complexity of the algorithm? Okay, but it all comes from here. The different types of algorithms that you can work on, they just have different A, B, and f of n's. And so far, I haven't found an interesting and well-known algorithm that goes into the third case. We found one in the first one, we found 2 in the second one, but I couldn't find one that fits into the third one. Now, can I manipulate A, B, and f of n to make it fit into the third case? Yes. But which algorithm is that? I don't know. I'm just making up these constants to make it fit. So that to me is not a whole lot of fun. I mean, it doesn't really connect it to anything that we know. Okay. So that's just kind of a follow-up from last week's discussion based on the master theorem. Is that okay so far? Okay, all right. So what we'll do today is to take a look at this algorithm. And to be more specific, we want to look at graphs. This is a graph, okay? This is a very easy way to look at a graph. It has got vertices, so when you look at A, B, C, all the way to E, they're called vertices or nodes. Okay, so when I accidentally slip and say node, you know that I actually mean vertices. Okay, points. Okay, where you can connect it. Is that okay? So in the graph, you have vertices. In this case, the vertices would be a set of A, B, C, D, E. Okay, that would be the set of all the vertices. Is that okay? And then we also have a set of edges. An edge is basically an arrow, in this case, going from one vertex to another vertex. So we have one vertex AB because there's a line, there's an arrow going from A to B. So here's a vertex AB. We have a vertex AC because there's a line connecting A to C, just like that. There are no vertices between C and E, so because you don't see a particular line connecting these two. Now, can we get from C to E? Yes, because there's an edge connecting C to B, and there's a different edge connecting B to E. So going through these two edges, C can actually go to E, but there's no direct edge going from C to E. Is that okay? All right. So the set of edges in this case, how many elements do we have in the set of edges?
8.
There are 8 edges. Okay, so let's do some counting here. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. So there are in fact 8 edges in this particular graph. So we have 5 vertices, 8 edges in this particular case. These edges are also directed. In other words, you have to follow the direction of the arrow. I'll give you an example. AE is one edge. Can we go from E back to A? No. Okay, so the edges are one way only. This is also called a digraph, which stands for directed graph. So when we talk about graphs, you can have edges that are bidirectional, in which case we just say it's a graph in general. But when the edges are directed, or they can only go in one direction, the graph itself is called a digraph, D-I-G-R-A-P-H. Are we still doing okay so far at this point with the concept of edges and vertices? Okay, all right. So you also see on the whiteboard or on the projector, we have HAE equals to 3, HBE equals to 1, and so on. Those are called heuristics. In other words, each one, HAE, is guesstimating. It's basically estimating from A to E what is the cost. Now we see that in this case, that's kind of pointless because we have an edge connecting A to E directly, which has a cost of 25. So when you see the numbers along an edge, it is representing the cost of an edge. Now the cost can correspond to time, can correspond to how much fuel, can correspond to how much money it will cost to go from one node to another node. And then the nodes can represent drop-off points. If you're driving a UPS truck, okay, it can represent all the drop-off points. So most of the time we want to look for the shortest path from one particular vertex to another vertex. So let's check out another heuristic here. Let's check out one that is really far from E. How about C? There you go. So when you look at the heuristics from C to E, it has a heuristic of 2, which means without even exploring the graph, okay, just by guessing, I'm guessing that C, it will cost me 2 units to go from vertex C to vertex E. Well, as it turns out, the shortest path is actually 3, so I was kind of close. The only requirement for these heuristics is to be quote-unquote admissible. Admissible is basically saying the heuristic is always underestimating the actual shortest path, or the cost of the shortest path. As long as the heuristic is underestimating, the Astar algorithm will be able to find the shortest path. Is that okay so far with these concepts? Yep.
What's the point of doing that though? You can just look at the edge that like C, if you just look at the first two, the only two edges deleted from it, you just pick the smallest one. So what's the point of the heuristic though?
The heuristic is kind of like a guide, so that if your heuristics are reasonable, you basically can avoid exploring a lot of vertices that are in the wrong, quote unquote, wrong direction.
Oh, so you just avoid going down the edge that costs 7, so you just avoid that path.
Yep. Yep. So heuristics is what makes the A-star algorithm different from Dijkstra's algorithm. And that's why I want to talk about the A-star algorithm, because Dijkstra's algorithm is exactly like A-star, but without heuristics. Or you can say the heuristics of everything is a 0, because it's always an underestimate. So that makes A-star a little bit more general compared to Dijkstra's algorithm. Yep.
Why is the heuristic from A to E?
Say again?
Why is the heuristic from
A to E. You mean why is it 3?
A to E?
It's just because without looking up the edge, the estimate is 3. So the estimate is way lower than the actual cost of the edge. But that's not wrong. I mean, it's okay. It's not a problem.
So is there any algorithm for the heuristic?
The only thing you want the heuristic is it's quick to compute. So you want heuristics to be very easy to compute. I can give you an example. Okay. Yep. Go ahead.
How do you get a heuristic?
Okay, that's a good question. I think my example will help you understand that. So we'll go to maps, and then we'll look up San Francisco. Oops, typo. But close enough. Okay, so when you look at a map of San Francisco, you can kind of look at each intersection or each house address as a vertex. Each potential destination is a vertex. So is every single so is every intersection, because with an intersection you can go into an intersection, but there are multiple ways of going out of an intersection. You can make a left turn, you can go straight, you can make a left turn. But in San Francisco, a lot of times you get one-way streets, you can only turn one way but not the other way, and so on and so forth. Right?
Yeah.
You definitely do not want to use a regular route, but use a diagram in San Francisco, because there are too many streets that are just one way. Is that okay? All right. So in this case, so let's say let's see if we can be more specific. So let's say we want to go from the 16th Avenue tiled steps to, I don't know, let's pick another landmark here, Union Square. Okay. So the heuristic is something that is easy to compute, doesn't take a lot of time, and it is always an underestimate of the actual distance. So a quick and easy way to do this, especially on the map, is just measuring the straight distance between those 2 points. Okay, let me say that one more time. You just draw a straight line, okay? You just draw a straight line from 16th Avenue tiled step to Union Square, and whatever that line, the distance of that line is going to be used as the heuristic. It's always an underestimate, right?
Yeah.
The actual distance is going to be a little bit more than that. Question?
Can you go back to the question for the example?
Yep. Oh, it's on the browser, just on a different tab. There we go.
So why is a heuristic from D to E to it's only one?
From D to E. From D to E, the actual edge is costing 3, but the heuristic is 2, so that's okay. Okay, so if you want to kind of look at the map again, okay, so let me pick. Okay, so let me pick a particular place where that makes sense. Okay, so let's take a look at this intersection versus this intersection here. Okay, the actual distance is going to be this much, but the heuristic is just an underestimate, which is the straight line distance. So that's why between any 2 vertices, you can have an edge connecting those 2 vertices, but it doesn't prevent you from having a heuristic as an estimate. Okay. Any other questions about what a heuristic is? It's just a rule of thumb that is quick, easy to compute, and it is always guaranteed to be an underestimate of the actual shortest path. Yep.
So you said that this algorithm works only if the shortest possible path is shorter than the actual path?
No, the estimated distance of the shortest path has to be always smaller than or equal to the actual shortest path. And go ahead.
Well, I think you'll probably get to this later, so if you will, just tell me to shut up. But what's
Okay.
the benefit of having the underestimate of the heuristic?
If the estimate is overestimating, then you can miss the optimal path. So that's why you always want the estimate to be an underestimate. Yep, go ahead.
And what if the actual path is the same length as the heuristic path?
That's okay. It only has to be less than or equal to. Okay, very good. Those are all very good questions. Anything else? Anything else before we move on? So let's just kind of review the concepts that we have talked about, and I'm going to put ourselves back onto the slide of the questions, okay, and also the algorithm itself, okay. So a graph is represented by a two-tuple. The first item or the first element in the two-tuple is V, which is the set of all the vertices. So in our case, in this example, is A, B, C, D, E. The second item in the two-tuple is E, which is the set of all the edges. Okay? Are we okay so far with those concepts? Vertices, edges, and when you combine those two, you have a graph. Is that okay? All right. So in this case, we also have a function, the distance function. The distance function is mapping the edges to real numbers. But to be more exact, these have to be non-negative real numbers. In other words, we are associating each edge with a non-negative real number to be the cost of that particular edge. Is that okay so far? So we are using functions again, because functions is a function is a very practical utilitarian concept, and we can use it in many situations. Anytime we have something to map to another set, a function can potentially be used. Okay. We also want to designate a particular start vertex, a particular destination vertex. So in this case, we have a start vertex being lowercase s, and then that destination vertex being lowercase x. Is that okay? Because the idea is, tell me how I can go from s to x in the shortest path. What is the shortest path to go from s to x? That really is the question. Okay? Are there any questions at this point about the terminology, what each symbol is representing? Go ahead.
What's R again?
R is real numbers. So we're just mapping each edge to a non-negative real number. Okay. So when you look at the heuristic is actually, it's better to use this as E, okay? So it is mapping, nope, I take it back. This is actually correct, okay? It's mapping every vertex to every other vertex using a function, and it is giving you a real number. So give me any two vertices in V, and what H would do is to say, okay, this is where you start, this is where you end. This is the estimate of how the distance between these two vertices. Is that okay? Are there any questions about what H is representing and why it is represented like this as a notation of a function? It takes two parameters. Both parameters are vertices, and is mapping those two vertices to a real number, which is always going to be an underestimate of the distance between those two vertices. Okay? Are we still okay so far with the discussion of the symbols? All right? So this is the actual algorithm. The algorithm has an initialization. This is the initialization. For each v in uppercase V, okay, does everybody understand what this type of control structure is going to do? It will take each element out of the set of all vertices and then do the following initialization with that particular vertex. If V that we choose, if the vertex that we have chosen is not the start vertex, then we want to initialize g of v to be infinity, f of v to be infinity. Now, these two are quote-unquote functions. In other words, it takes a single parameter, which is a vertex, and it gives you a real number. Now, what is g actually doing? What is f actually doing? We'll talk about that later. Okay. One is a through, estimate. Going through me to the destination is going to cost this much, and the other one is just how much does it cost to get to B. Okay, so we'll talk about that later. What if V is the same as S? In other words, what about the else case? The else case is saying V is a start vertex. So when V is a start vertex, then G of V is initialized to be 0. It doesn't cost anything to get to the destination. It doesn't cost anything to go from the start vertex to this vertex, because this is the start vertex. So obviously the distance is going to be 0, because we are in fact at the start vertex. For everything else, okay, we want to initialize, I take it back. F of V is the estimate, okay? Through this particular vertex, what is the current estimate to get to the destination? Well, since V in this case is the start vertex, so that means the estimate to get to the destination, which is x, is just h, which is the heuristic of going from the start vertex S to the destination vertex, which is V. I mean x in this case. Is that okay? So if you want to draw a picture, okay, of what kind of problem we are trying to solve here, we have vertices, we have edges connecting the vertices, and so on. We designate one particular one as S, which is the start vertex, and then we designate another one as vertex X, which is the destination. So the question is, what is the shortest path to go from vertex S to vertex X? Is that okay? All right. So from the initialization, we can see what G is really doing. G of V is actually the distance from the starting vertex S to V, the actual distance. It's not an estimate, that's the actual distance. It's the actual known shortest distance from S to the vertex V, whatever the V is. Is that okay? All right. What about F then? F is kind of a combination of this and the heuristic to the destination. So F of V is the estimated distance from the start vertex S through V to X. Okay, so let's pick one V here. Okay, let's pick this guy to be V. Okay, so let's say this is V. G of V is actually, okay, what is the known shortest path to go from the start vertex to vertex V? That is G of V. Okay? What is F of V? F of V is what is the estimated shortest distance to go from the start vertex through vertex V to the destination X. That is F of V. Okay, is that okay so far? Okay. So the terminology takes a little bit of getting used to, but when we get to the algorithm, I think it will be kind of clear what this is going to do. So this is just the initialization. For everything else, we initialize both G and V, G of V and F of V to infinity. In other words, before we run the algorithm, we pick any vertices other than the start vertex and go, okay, let's pick this one here. Without knowing how the edges are distributed and what are the costs of these edges, we just say that it's infinity. It's infinity to go from the start vertex to this vertex. It will also be infinity to go from the start vertex through this vertex to the destination. So I use infinity to initialize all of the other G and F's. Everything other than the start vertex is initialized with infinity. Is that okay? We'll trace the algorithm, okay? So don't worry, okay? We will trace the algorithm and find out how we update G and V as we explore the graph. There's one more thing that we are doing to do the initialization. Prev is or prev, okay, previous, is actually somewhat not a function. It is only here to remember, in order to go back to the start state, who's my previous? Okay, so they're all initialized to undefined. Okay? So if you have 5 vertices, all 5 vertices will define the previous vertex to be undefined. But they will be defined as we go through the algorithm. This is a way for us to track from the destination to track the shortest path back to the start vertex. Okay, shall we move on? Okay. There are many variants of the A-star algorithm. This is just one of them. We do the initialization of a set O, uppercase O, to be only consisting with the start vertex. And then what we do is we have a nested loop here. The outer loop is a while loop. It is basically saying as long as the O set is not empty, we'll do the following. And then inside, the first thing we do is we want to find the shortest path. Let me take it back. We want to find a vertex C inside the set O, not in the set V, such that f of C has the least value amongst all of the other vertices in O. So we're finding the vertex that has the shortest f value within the set O. And then we choose that one, and then after we choose that particular vertex, the first thing we do is we remove it from the set O, and then we look at all the neighbors, okay? So when we look at all the neighbors n of V, because C of Cn is an edge that we already know. Is it possible that C has no outgoing edges? It has no neighbors. It's entirely possible, okay? In which case this for loop would not have anything to do. It's also possible that C is connected to many other vertices, so you have to go through this for loop many, many times, and then for each neighbor, you have to evaluate the following. So the first thing we do within this loop here is to evaluate and store a value into the temporary variable t. In other words, t is just a shorthand, so I don't have to repeat using t multiple times. So what t really is g of c plus d cn. Okay, so let's take a look at what is g of c again and what is d cn, and why is that particularly important to us. Okay, so when you look at the whiteboard, you can already see that g of v is the actual known shortest path or shortest distance from the start state S to the vertex V. Okay? So that accounts for this part here. G of C is the actual known shortest, or I should say, the distance of the known shortest path from the start vertex to vertex C. That's what the highlighted part is. Is that okay? But we already know that C and N are connected by an edge. How do we know that? How do we know that C and N are connected by an edge? It's inside the for loop, right? What is the qualification of N? Now, the first qualification is easy. Vertex n has to be in the set V. Okay, that's easy. What about the second part? Such that Cn as a two-tuple is in E. What does that mean?
There's an edge.
There's an edge going from
C to N.
C to N. Okay, so there is an edge going from C to N. So when we look at the second component of T, which is dCn, what is D again? What is that function D doing? If you scroll up a little bit, you will see that. Okay, you don't have the document, so let me scroll a little bit. I'll share the document so that you can actually see that. What is D again? Look at the first line. It describes what D is.
Map speed of the real edges.
It's the cost.
Yeah.
It's mapping the cost of an edge to real numbers. Like this edge is costing me 5 units. This edge is costing me 3 units, and so on. Okay. So if we keep that in mind, and we can actually display both at the same time. Okay. So when you look at T, what do you think is T really representing at this point? The first part, G of C, is saying this is the cost of the shortest path known at this point from the start vertex to C. Yep.
It's T is like the cost of all the neighbors of C from S.
Okay. So let's see whether we can do. Let's look at this graph here. Okay. So let's say we choose this one to be C, and then it connects to a few vertices. Is that okay? So let's call this C1. I mean N1, N2, and N3 for neighbors. Okay. G of C is telling us one thing. G of C is telling us, oh, we know a particular path, the current known shortest path to go from the start vertex to C is going to cost us G of C. That's what G of C is representing. Okay? By adding the cost of the edge C to N1 to this number, what are we getting?
The cost from the start to any node from C.
Well, we are getting the cost of a path, not necessarily the shortest, but we're getting the cost of a path from the start vertex through C to N1, N2, and N3. Okay, well, for each iteration, it will do only one computation. Okay, but we are figuring out the cost of a particular path. Is it going to be the shortest? We don't know at this point. Okay, it may be the shortest, may not be the shortest. Okay, but that's okay. It is the cost of a path. Okay, so you might want to kind of write down in your notes, okay, or when you listen to the lecture again, you can write it down at that point. T is representing the cost of a path going from the start vertex through vertex C to vertex N. C and N are connected by an edge. Okay. Then what do we want to do with T? Okay, that's the next question. So now we have a conditional statement. This is where some of the other implementations has a slightly more complicated expression in the conditional statement. I just make it really easy. I just make it a very simple less than relationship. But what is the significance? What is G of N? We know what is C of N. What is G of C? What is G of N?
Shortest known path to N.
Yep, shortest known path to N from the start vertex. What if T is less than G of N? Why is that important to me?
That means you go to a new path that if the N is short.
Exactly. Okay? So if this condition is true, that means what I thought was the shortest path is not the shortest path anymore. Okay, now that is important because now I got stuff to do. The first thing I need to do is I'm adding N, not C, back to the set O. Okay? Because I'm saying that, hey, what we knew about this vertex, being, what we knew about the shortest path from the start vertex to N is not really the shortest. That might change the distances of multiple vertices connected to N. So I better recalculate some of that stuff. So we have to add N back into O, like this, okay? Basically to recompute everything else that is connected to n. The second thing we want to do is to update n, okay? And say that, oh, you know what? We just found a shorter path to get to n, and it is going through C. So that's why I'm updating the previous of n to be C. If you have gone through linked list in your cisp440 class, this is basically a pointer going backwards, okay? Who got to me? Who led to me? Okay, in this case, n has a previous of C because we found that this path is shorter than the path that we have already explored before. Is that okay? How about the, yeah, go ahead.
So when you said like you were adding n back to
The set O.
yeah, like where is it like first initialized like n instead of
Okay, which one? You mean the set O itself? How was it initialized?
yeah.
It's on line 16. O is just initialized with a start vertex to begin with. But every single time we get to this conditional statement, we potentially can add the neighbors of a particular vertex into the set O. And that's how set O gets bigger and bigger and bigger, and then eventually it will get smaller and smaller until it becomes the empty set, then we are done. Okay. What about the third line inside the conditional statement? What is this doing? Why are we updating g of n, and why are we using that t?
T is
Cost, the total
Yeah.
cost of a
Yeah.
path, but we know that it is shorter than what we thought was the shortest way, right? So we have to update it. Is that okay? It is the rationale of this statement that is important, okay? It's not what it does, it is the context. Why are we doing this? That is important. Can you see how this condition relates to this assignment statement? The condition says, hey, we just found a shorter path. Okay? So what do we have to do when we just find a shorter path?
Log in, this is the shortest one.
We have to remember, exactly, we have to remember what we thought was the shortest distance from the start vertex to here was not true. This is the shorter path. This is the cost of the shortest path at this point. That's why we have to update it. Yep.
Still got confused on why you have to set previous
Previous
of n.
of n, so that we can back trace our way back to the start state. It doesn't serve any purpose when we are finding the shortest path, but once you have found the shortest path, you need to retrace, because by the time you terminate the loop, you'll be at your destination. The question is, how did I get to the destination? You have to follow the previous along the way. So the previous basically form a chain to go back to the previous, all the way back to the start state. Okay? So we only have one more statement left inside the conditional statement. Okay? What do you think this one is doing? Oh, by the way, when do we use f? I mean, f doesn't seem to be that useful. It's only updated here, but when do we actually make use or read the value of f of something? Which line are we talking about?
Line after the while statement.
Line 18? Okay. So line 18 is the only line that makes use of the value of f of something. This, line 26, is the only line that will assign a new value or update f of n or f of a particular vertex. So what are we updating that thing to? Let's take a look at the components of this addition. What is the first component? What is g of n? We just updated it. What is that?
Now the shortest path.
The shortest path.
Is the cost of the shortest path from the start vertex to vertex n. Okay, very good. What about the second component? What is h and x? What is that representing?
It's the heuristic of n to x, which is the n.
Which is the destination. Very good. Okay, so f of n is fulfilling its purpose, right? It's fulfilling the purpose of being the estimated distance from the start vertex through the vertex that we are dealing with to the destination. But why is that important? How does this have anything to do with line 18? I mean, why? Why are we updating f and why are we using f on line 18? We are looking for the most promising vertex. Okay? In other words, we're looking at all the vertices that we are supposed to evaluate and go like, okay, which one is the most promising one? So what we do is we look at this equation here, which is what is the estimated cost of the shortest path from the start vertex through this particular vertex to the destination. Okay. Now I know this is going to be a little bit painful for some people. Okay, it's not painful for me because I've never tried. Yep, go ahead.
This is like, it's kind of like how like GPS like routing, GPS routing works. Like, is it just checking like all the possible routes until, and then just.
But it's not checking all the possible routes. That's the whole thing. With Astar, the whole point is if you have your heuristic being somewhat useful, it will leave a lot of those vertices unexplored because they're not promising enough
So
to
it's
be
just checking
evaluated.
the routes within the realm of a direct line between one and the other.
Yep, it will only evaluate the promising ones. Okay, so I thought about whether to use this as an example or not, but I think it's actually a pretty good example to use. Okay, so when you look at f of something as as a metric to evaluate who should get a scholarship. Okay, I'm not sure how many of you have applied for scholarship. If you have not, you should do it because we have got more scholarships than applicants on this campus. Okay, nobody is responding to that. It's like, money, I don't need it. I don't need money. Okay, let me say that one more time, okay? We have more scholarships than there are applicants. So using the pigeonhole principle, what can you conclude out of that statement? We got more pigeonholes than there are pigeons.
It means that there's enough money to go around, anyone that applies for it.
Exactly, every pigeon can get a nest without fighting. Not for long?
Is that true, or is it like real statement?
Oh, trust me,
Is that
of this class, I would say about 5% would actually try to do something right out of the class. By the time they get home, they would have forgotten about the whole thing. Okay, but so I'm going to use it as an example. Okay, so G of n is the current GPA of a student. Okay, that is the proven current fact about the performance of that particular student. That's G of n. F of n is combining the GPA with an estimate based on the professor's observation of how far that student can go in graduate school or in a four-year university and stuff like that. So together, okay, F of n is using the current known facts, okay, current GPA of a student combined with a projected GPA to become a metric to evaluate who seems to be the most promising student to be explored next, to be given a scholarship next. Is that making any sense?
Yeah, it's just totally inhumane.
So we are not only using the current GPA to make a decision, we are also taking into consideration what do you think of this student, of the potential of this student in the future? That is also, that's H, that's the heuristic. Yep, go ahead.
So does that mean the higher f of n, the better?
No, in this case, the smaller the better. Because when you're looking for a path, you're looking for the shortest path. Okay? Are we doing okay so far as the rationale of these lines of code? Because that is more important than the actual mechanical aspect of the algorithm. You okay with this? Okay? So, my first question, which is actually one of the questions, in this particular test, is can we get into an infinite loop and never get out of this algorithm? That's the first question. Now, in order to answer the question, I have to give you something first, okay? So what I can tell you ahead of time is all the heuristic functions are non-negative. Okay, they can be as bad as 0 or as good as 0 because the shorter the better, right? So h of something has to be at least 0, but it can be positive. The cost of edges are also guaranteed to be non-negative, and you can even assume that they're non-zero. Okay? So given those two facts, can you look at this algorithm and say, well, is it possible for us to get into an infinite loop in this algorithm? What will it take to get into an infinite loop in this algorithm? And why is that not possible? So at first glance, it is not possible to get into an infinite loop because whatever we pick out to be vertex C is immediately removed from that set. So the set seems to be getting smaller and smaller and smaller. And so it cannot be an infinite loop. Every time we go through this iteration, we are removing one element from O, and therefore it cannot get any bigger. But that's a fallacy, because inside the for loop, inside the for each loop, there is a potential to add a particular vertex back into set O, and as a result, so the question is, how come I cannot infinitely remove it from O and then add it back to O, remove it from O, add it back to O, and so on? Because if you think about any type of infinite loop in this logic, there has to be a particular vertex, at least one, that you're removing and then adding back, removing and adding back to a big O. Otherwise, there won't be an infinite loop. Yes?
Wouldn't it be because you're updating the G of n as well? So you can
Very good. Good job. Because to get to this part, to get to line 23, this condition has to be true. Right? Wait, hold on a second here. If that condition, what is the big deal of that condition has to be true in order to get to line 23 to add a particular vertex back into big O? Why is that a big deal? Yep.
Because if you went through again and tried to and wanted to re-add it, then the T would equal the G of n, so then it wouldn't hit the loop. It would hit the if statement.
It has to be smaller. You have to find a better way to.
Yeah, well, it has to be smaller to go. It has to be smaller to go in, but
right.
The second time around, even if it had the same O,
yeah.
T would now equal G of n, which means that if statement wouldn't happen. So then that next element.
But it may not. But that vertex n can have multiple vertices that connect to it. So one path from one of the vertex before that can have a higher path initially. We just chose the wrong path. So you can revisit the same vertex multiple times, but not infinitely. Yes?
Because no matter how many because at some point you'll find the best possible path, and then you'll never have a value that's less than the best possible path because there's a finite number of edges.
Yes.
So there's a best possible edge, and you'll never find a T less than that best possible edge.
Exactly. The number of possible ways to go from the start vertex through a particular vertex is finite. So even if you make the worst possible choice each time, so that another path is better and another path is better, there are only so many paths that can be better than the worst path, because there's a fixed number of paths to go from the start vertex through a particular vertex. Okay? So it cannot be infinite. Okay? If that cannot be infinite, then this algorithm has to terminate, because you cannot add a vertex back to big O indefinitely. There's only so many times you can add a vertex back into big O. Okay, so this algorithm is guaranteed to terminate. It cannot get into an infinite loop. Okay, very good. Again, glad that you guys are applying that reasoning, even though this is the first time that you saw this algorithm. You're already starting to pick up, okay, that's not possible because of that condition. Okay, so that's good. That is a good thing. Okay. So the next thing we want to do is to kind of go through this algorithm and apply that to the graph in the question. Okay. So this might get a little bit messy because I will need a mechanism to kind of log this and also update things at the same time. So what I'll do is I'm going to try to do something like this. Okay, I'm going to resize this window so that we can look at different things at the same time. And I would use mouse pad on the side to keep track of things. Okay. All right, so we want to go through this algorithm, and I'm not going to do a line-by-line trace because that's just going to be super duper too tedious. So what we'll do is we'll just go ahead and figure out, okay, how are we initializing the G values of all the vertices, and how are we initializing all the F values of the vertices. But before we do that, we also have to know which one is the start. So according to the question, there is a designated start vertex. And okay, which vertex is the start vertex? Oh, okay, it says error here, but it's really not an error. There we go. So the start vertex is A, the end vertex is E. Okay, the destination is E. Is that okay? All right. So let's go ahead and look at the G values of these things. What is G of A? G of A is the cost of the known shortest path from the start vertex to vertex A. Oh, which one was our start vertex again? A itself. So what is the cost to go from A to A? 0, very good. Okay, so that's kind of intuitive. What about F of A? F of A is G of A plus the heuristic of going from A to E. So what is the heuristic of going from A to E? 3. So 3, okay, so that makes F of A equals to 3. The other ones are easy. They're all infinity. So this is how we are initializing these functions to begin with. Oh, there's also one more thing that we have to initialize. So the previous of A is unknown. Okay, there we go. I'm just going to use UNK for unknown because that's the amount of space that I got here. Okay. G of C is infinite. F of C is infinite. Previous of C is unknown. And then just gotta be a little bit lazy here. E, 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 and E. There we go. So even though E is the end state or the destination state, it doesn't get anything special. Only the start vertex is special. Is that okay? Yep, go ahead.
Is it because E is the end state, that's why you use F of A?
Is that because
Because E is the end state, you said?
it is the destination state? Yep.
Destination
But it doesn't get any special treatment. It doesn't have any. It has infinity as G, F, and it also has unknown as the previous, just like every other vertex.
So, is that why you use E to find F of A? So it has to be equal to E?
Yes. 2E, not 3. Yep. Mm-hmm.
Okay, so you're saying we're initializing it to infinite, but how would we actually do that in a program? You're gonna initialize something to an infinite value.
Well, it depends on what is the type. Okay, if you're using ints, you can use max int, which is defined in standard int.h. If you're using floating point number, there is a representation of infinity as a part of the double precision floating point numbers. They actually chose a particular bit pattern to represent the quote-unquote quantity of infinity. So there is a way to represent infinity that is larger than everything else. Yep, go ahead.
Where does F of A 3 coming from?
It is because of the way we do the initialization in the code. Okay, so when you look at the code here, if it is the start state, then the heuristic of going from the start state to the destination is used as f of the start state or start vertex. Okay? All right. So now we are ready to go into the algorithm, but we have to do a little bit of initialization first on line 16. So on line 16, we initialize big O to consist of one single element, which is the start vertex. The start vertex in our example is vertex A, so that's why vertex A is the only element in the set at this point. Okay, so now we want to look at the first while loop, okay, or first while loop iteration, first iteration of the while loop, okay. Okay, so what are we going to do here? Is it empty? No, we have one single element in it, so it cannot be empty. In that case, I want to find the vertex in this set that has the lowest, the smallest f value. I don't even have to look, and I know which one I'm supposed to pick, because there's only one element, we have to choose that one, right? So without even comparing, I can already see that this is going to be confusing because we have vertex C, but we also have a variable C in this case. So I'm going to use a var C to represent variable C, which is this guy here. So variable C has no choice but to be the value of vertex A. Is that okay? Because that's the only element. But after this, we also want to remove that element from big O. So big O is now an empty set. So now we go into the for each vertex and blah, blah, blah thing here, okay? So iteration 1 of for each loop, okay? So we look at vertex A, and then we go like, okay, who are the neighbors of vertex A? Well, vertex A turns out to have a lot of neighbors, okay? Including the destination state. So you might think, oh, so this is going to be easy problem to solve because in one single loop, we just find it, okay? In fact, let's explore E first, okay? Because when I say for each, there's no particular order that I have to go through. I can choose E to be the first neighbor of A to explore. Okay, so let's do that. Okay, so I choose N, variable N, which is the neighbor, to be E. Okay, what are we going to do with the algorithm now that we have chosen that? Okay, so once we have chosen a particular vertex as the neighbor of the vertex that we are dealing with, the first thing we want to do is to compute T. Okay, so let's go ahead and do that. So T is going to be, in this case, G of A plus the edge, the cost of the edge going from A to E. And what is that going to be? Just based on what you see on the screen right now, can you help me compute T? G of A is a 0. And the edge, we just saw the edge. What is the cost of the edge AE? 25. Okay, so what is 3 plus 25? Oh, 0 plus 25, sorry. Just 25. Okay. Cool. Is 25, are we going to have a less than relationship with this comparison? Is 25 less than G of E at this point? What is G of E at this point? Infinity. Anything is less than infinity. Cool. So that condition is going to be true. Okay. Cool. So then what are we going to do? We follow exactly this routine here. We say the big O is now one element more than before. It now has element E in it, which is our destination vertex. The previous of E is A. Is that okay? And then G of E is 25. Is that okay? Because T is 25, so we use that to update G of E. And then the last one is F of E is also just 25, because the heuristic to go from E to E is 0. Makes sense. Doesn't cost you anything to go from vertex E to itself. Are we okay so far with these updates? Okay. All right. So instead of looking at the updates like this, let's go ahead and actually update the stuff up here. Okay, so this is 25. This is now 25. And this is not unknown anymore. This is just A. Okay. And I think those are the only updates that we did. So what I'll do is I'm going to copy and paste this just so that it's easier for us to follow those values around. Okay, there we go. Now we are on to the second iteration of the for loop. Iteration 2 of the for each loop. Okay. So which neighbor of A do you want to choose as the next one to explore? We still have 3 more to choose from, so you guys can let me know which one you want to choose. C? Okay, so let's pick C as an example. Okay. So if we choose C as the neighbor of A to explore, then we say var n is C in this case, and then we just go through the algorithm to figure out what we need to do. The first thing is to compute T. So T is G of C, which is A in this case, plus the cost of the edge going from A to C, which is 1. Okay? G of A is a 0, DAC is a 1, so that means this T is a 1. It makes sense, right? The known shortest path, or the cost of the known shortest path to go from A to C has a cost of 1. That makes sense to us, right? Okay. Then we have the conditional statement. Is 1 less than G of C, which is infinity? Yep, okay, 1 is definitely less than infinity. So we go through all this stuff here. Big O is now E comma C, because we just add this, union this into the set. The previous of C is A. G of C is 1. F of C is 1 plus the heuristic of going from C to E, which is 2. So it is 1 plus 2, which is 3. Are we okay with this? Do we understand why F of C is 3? Because that's an estimation. Okay? It is an estimation of, if I go from A through C to E, what is the current best estimate of that path? It is what is known to us, which is from A to C, plus the heuristic, which is an estimate from C to E, but according to our heuristic function, HCE is 2. So that's why it's 1 plus 2, which is 3. Are we okay so far?
Could you go back up to the pseudocode or the just with okay.
Is that okay? All right, cool. All right. So as we did before, we're going to update this number here to be a 1. And we'll update this number here to be a 3. And we'll update this previous to be a, just like that. Okay. Which one do you want to pick next? Iteration 3 of the for each loop. Which neighbor do you want to choose this time? We have 2 more neighbors that we can choose from. We can choose B or D. Pick one. B. Okay, so we have this feels like Wheel of Fortune. But vowels are not special in this case. Okay, so we will choose B here. Okay, so once again, we compute what is T. So T is G of A, which is known to be 0, plus D, A, D. The edge AD has a cost of 9. 0 plus 9 is 9. 9 is less than infinity, which is G of D at this point. Oh, we chose B, right?
B is fine.
Okay, let's change this to D.
We already started.
Yeah, I just. So we're choosing D to be the one explored, to be explored. So now this is actually 4, but it's okay because 4 is, nope, not 9 is fine. Never mind. Because we are looking down here. Okay, so that's good, that's good. So we're going to add that into the big O. So now the big O has E, C, and then D as elements. The previous of D is going to be A. G of D is going to be 9. And then F of D is 9 plus the heuristic going from D to E, which is 2. So the total is 11. Okay? So now we go back here and update these numbers. So this is no longer infinity, it is 9. This is 11. And this is A. So we'll go ahead and copy and paste this just so that it's easier for us to see it like this. Okay, we have one last iteration. So the last iteration, which is iteration 4 of the for each loop, we have no choice in this case because the last neighbor that we have to explore is B. T is G of A plus D of AB. G of A is 0. The edge of AB has a cost of 4. 4 is less than G of B because that's infinity. Anything is less than infinity. So we'll update all of these things. So first of all, we add it to big O. So big O now has E, C, D, and B as elements. Previous of B is A. G of B is 4. And then F of B is 4 plus the heuristic of BE. According to this, it is 1. So it's 4 plus 1, which is 5. And that concludes the first while iteration, because this is concluding the last iteration of the for each loop, but it's also, as a result, concluding the first iteration of the while loop. Is that okay? Because the while loop has the for loop as the last operation, and we are done with the for loop at this point. Is that okay? All right. So let me just update all of these things first. So B has, I think that's a 4. This is a 5. And this is A. Oops. And then we'll copy and paste this to the end. Okay. So you go back to line 17 at this point, and you say, well, can we go? Are we done? Nope, we're not done, because big O has 4 elements now. Okay, so we have to go to iteration 2 of the while loop, the outer loop. So this time, which one am I going to pick next? I have to pick a vertex from big O, and we got 4 to choose from. But I cannot just randomly pick one. I have to pick the one with the least F value. So when you look at all the F values, which one is the smallest of all the elements in big O at this point? C seems to be the most promising because it has got the smallest value. So var C is now C. And then what we need to do is to change big O so that big O does not have C anymore. So we remove that, so it only has E, D, B remaining. And now we go to the inner for each loop. So we have iteration 1 of the for each loop. So we look at vertex C and go like, okay, who are your neighbors? It has got 2 neighbors. It got one neighbor B and one got one neighbor D. Which one do you guys want to use first? Pick one. Sorry? Go ahead. E? D. Okay, so we'll pick D. All right, so we'll say var n, which is the neighbor, is D. So first thing to do is to compute the t value. So the t value is based on G of C, which is 1, plus the cost of the edge going from C to D in this case. So according to this diagram, the cost of that edge is 7. So that is 1 plus 7, which is 8. So now we have to evaluate the conditional statement. Is T less than G of D? That is the question. What do you think? Just beat it by 1, right? Because G of D has a value of 9 and T has a value of 8. In other words, what we thought was the shortest path is not the shortest path anymore. We just found a shorter path to go from the start state to vertex D in this case. Is that okay? So this is important. Because now we get to update all of those things again. We say, oh, we better double check all the things that are connected from vertex D. So we're going to put it back into the big O set. It's already in the big O set. That's okay. Okay, it's not a big deal. The second thing we have to do, according to the algorithm, is to update the previous. So we say the previous of D is no longer what it used to be. It used to be A. No. That's not the shortest path anymore. The shorter path is going through C. Okay? So this is important because we are actually looking at the algorithm working to correct itself. Okay? It made the wrong decision and thought that the shortest path is going through that first. Nope, we just found a shorter path. We are now correcting it. We also have to update G of D. So G of D is just updated to T, which is 8 in this case. And then F of D is 8 plus the heuristic to go from D to E, which is 2. So that is now 10, which means we have to look at these numbers and update these. So let me go ahead and copy and paste, and then fix the values that we just changed. So G of D is 8, F of D is 10, the previous of D is now C. Is that okay? So I don't think we have enough time to finish this today. I can finish this entire iteration of the while, but you guys can finish this when you get home, okay? So use this opportunity to kind of use the same approach, walk through the algorithm. It won't take you too long, okay? It's just kind of tedious. But it won't take you too long, so that on Thursday we can come back and you guys can understand, how the algorithm works. Okay, this one is kind of interesting. I set up the heuristics to misguide it. Okay, so the heuristics are set up so that you can explore the same vertex several times. So you will go through that exercise when you follow the algorithm. Yep.
The heuristics always need to be given to us?
Say it one more time. The heuristics? Yes. So the heuristics tend to be something that's easy to compute, and is always guaranteed to be an underestimate. Yep.
How do you get
Because it has the least F value at the time. Okay. So it's not something that you have to turn in, but I want you guys to finish this algorithm, finish tracing it, and I will continue to do it on Thursday as well. So that way you can cross-check your solution to my solution. It may not be the same because the way we choose the neighbors won't be the same, but when you look at the outer while loop, it should be the same, because we're always choosing the one with the least F value. So I better save this file because otherwise I won't be able to do it again on Thursday.
Just to make sure, is our lowest final grade graph or?
Yes.
So at the end of that while, you will have found the shortest path to every vertex from A.
You would have explored all the promises.
So you wouldn't have found the shortest one from A to all the vertexes? Because I know we're trying to get to the destination, but it looks like it's grabbing it to all of the everything that it's just because it's going for each neighboring node around each or vertex around each vertex.